Thus far, you should be comfortable determining the number of protons and neutrons in a nucleus from symbols that are written like this. If you recall, this top number is called the mass number, and it represents the number of protons plus neutrons. And this is called the Z number, or the atomic number, which represents the number of protons. Now the Z could be written down here, but on the periodic table it's typically written in the upper left corner or right above the letter symbol. For this particular video, I want to keep focus on the nucleus and discuss patterns of nuclear stability and something called the belt of stability. Okay, if you're titling your notes, again, this is General Chemistry 1, Unit 2, where we talk about atoms in the periodic table, and video 02D50, looking at nuclear stability. There are two phrases that you might be familiar with concerning the charge of the particles in an atom. The first phrase is opposites attract. And for instance, if you have a nucleus that has protons and neutrons, that nucleus is going to be positively charged, and you'll have an attraction to the electron, and vice versa. It's beyond the scope of this video, but even though there's an attraction here, the electron can't be on top of the proton or directly next to the proton. You'll have a maximum or optimal distance between the proton and the electron. So, besides understanding that opposites attract, you've probably also heard the term like charges repel. And that is of concern about nuclear stability because the nucleus has typically many protons that are in close proximity of each other. Let me see if I could focus this a little bit better. Okay, so we do have plus repulsion. Okay. So how does the nucleus stay together when you have this positive charge repulsion? Well, you have neutrons, and the neutrons help hold the nucleus together. And how can we represent that? We could represent that with a bunch of protons. So this is going to be representing protons. And you know that neutrons are also in the nucleus for most atoms. And we're going to learn patterns and trends as to determine whether that nucleus is stable or not, depending on the number of protons and neutrons. So let's give a couple of rules under nuclear stability. And rule number, did I number these? Yeah, let's say rule number 1. For elements of low atomic mass, or atomic number, and the cutoff will be 20. So elements below atomic number. What is that? That's Z. Z is either going to be less than or equal to 20. Okay. Let's take a look at the periodic table real quick. So elements that are here, there's 20 protons. 20 or less are going to have nuclei that are stable if the neutron to proton ratio is close to 1. Let me write that down for you. For elements with low atomic number, Z less than or equal to 20, if the neutron to proton ratio is close to 1, or 1 exactly, that will be considered a stable nuclei. It's not going to fall apart, in other words. Let's go to, and let's put a little reminder. Element 20 is calcium. Okay, number 2. As the atomic number increases, you need more neutrons. And the N to P ratio increases. To what? To maybe 1.3, to maybe 1.5. Okay, we'll see a chart where we see this increase in the neutron to proton ratio. So for instance, if, let's use 1.5. So let's say you have a larger atom. Let's take 40, for instance, zirconium. And you want a neutron to proton ratio of 1.5, you would notice that zirconiums that have, what's 1.5 of 40? 60. 60 neutrons and 40 protons, that is very likely to be stable because the neutron to proton ratio is 1.5. So let's give an example of that. If you have 40 protons and your ratio is 1.5, that will give you 60 neutrons. Right? You just multiply 40 times 1.5. This 40 protons is zirconium. You would expect this isotope to be stable. It won't fall apart. You could almost, well, not almost, you could say that it's not radioactive. It won't emit radiation. Won't fall apart and emit. We haven't talked much yet about radiation, and to tell you the truth, we wouldn't talk a lot about it or go too in depth until General Chemistry 2, but we'll introduce it here. Number 3. I'm going to give you a couple numbers to memorize. If a nucleus has, memorize these numbers, 2, 8, 20, 50, 82, or 126. If a nucleus has 2, 8, 20, 50, 82, or 126 protons or neutrons, that atom nuclei is likely stable. Okay. Meaning that it's not radioactive and it won't fall apart and emit radiation. And let me give you an example. An example is tin. Tin has a symbol of Sn. And if you look for SN, SN is right there, 50. Has 50 protons. What that means is that since it matches one of these numbers, any or most isotopes of tin will be stable. Meaning, most isotopes that can be obtained. Most isotopes of tin are stable. Number 4. This is a weird one. Of the combinations of odd and even protons and neutrons. The category that has the most stable isotopes is even protons with even neutrons. Like even amounts, 2, 4, 6, 8, etc. Again, it's a little bit beyond the scope of this video, especially a very early unit like Unit 2, to explain why these trends are true. And actually, I totally forgot. These numbers that I would want my students to memorize, these are called magic numbers. Magic numbers or magic stability numbers, but we'll just call them magic numbers. Okay. Alright, so we're not going to give any explanations for these trends. These are just trends that you would want to be aware of and be able to use to identify whether an isotope is stable or not. We have one more rule, rule number 5. Uh-oh, let me just double check this rule. Okay. All isotopes of elements with atomic number greater than 82 they're considered radioactive. Okay, so I do know that that is in contradiction to our actually it's not in contradiction. So 82, if it has 82 protons, the nuclei is stable. If it's greater than 82, you're going to consider it radioactive. Okay, this is atomic number, except for 126. Actually, let me double check what 126 is. Oh, that doesn't make any sense. There is no element with 126 protons. Okay, so this 126 most likely is going to be the number of neutrons. So there are isotopes in the universe with 126 neutrons. You're going to consider that stable. Okay. And I think that's it for the rules. Let me just double check. Yeah, that's it for the rules. Again, just be familiar with them and learn how to apply them if, for instance, you're given a element or isotope that has, let's pick one here, radium is over 82. So that's, most isotopes of radium are going to be radioactive. But let's take, for instance, molybdenum, MO, 42. 42 is not a magic number, okay? But if it has a high neutron to proton ratio, then isotopes of molybdenum with a high neutron to proton ratio would be stable. So where's this cutoff? Like, how do we know what the ratio of neutron to proton should be for a nuclei to be stable? And that comes from something called the belt of stability. Let me show you an example of a belt of stability image. And let's see. Okay. Remember, one of the trends was if the atomic number is 20 or less, if your neutron to proton ratio is close to 1, then that isotope is stable. So here is 20 protons, and see, a lot of the shaded region represents isotopes that are stable, and that shaded region is right on top of the 1-to-1 ratio line. Now, we said that as you get higher in atomic number, the ratio has to grow and increase. So here we have a neutron to proton ratio of 1.3 to 1, because it's a higher atomic number. If you get even higher, look at lead. Lead has a proton count of 82, and now in the belt of stability, the ratio between neutrons and protons is now 1.5. Okay, so anything that's within the shaded region is a stable nuclei. Okay. Let me jot that down. Okay. Any isotope with a what? With a proton and neutron count within the belt of stability, that shaded region that we saw, that isotope is stable. Now I want to go over, those are the rules, those are the trends, and we've seen the belt of stability. I just want to briefly look at what it means to be radioactive. And if isotope is radioactive, it will start to degrade. And you've heard of radioactive elements having a half-life. It's the amount of time needed for half of that radioactivity to be emitted. But let's not worry about half-life. If isotope is unstable, and for now we're going to make that synonymous with radioactive. Okay. There's instability in the nucleus. It's going to emit radiation. Emits radiation. And let me show you 3 types of radiation. Now, the 3 types of radiation can be characterized by how they act in an electric field. So, for instance, if you have here in a lead box something radioactive, and here's the lead box. The lead box can deflect radiation, but we'll have a little hole here, and it starts to emit radiation this way. If you have a system where, or a setup where you have an electrical charge, a plus here and a minus here, then your emitted radiation can be deflected in two different ways or not deflected at all. So if it's deflected towards the positive plate, okay, it is called a beta particle or beta ray. So a couple names, beta particle or beta ray, and that is positively charged. Oh, no, not positively charged. It's negatively charged because it's attracted to the positive plate. If it's attracted to the negative plate, so it will start to bend downward, that's called an alpha particle. Okay, we have beta and we have alpha, or alpha ray, and that's positively charged. Lastly, if there's no deflection, that means the emitted radiation has no charge, and that is called a gamma. I don't think people use particle, they call them gamma rays, and it's electrically neutral. Now I do want to mention that those of you who have studied radiation and these types of emissions may know these a little more specifically. For instance, an alpha particle is actually a helium nuclei. Let's not worry about that. Again, that will be covered much later, likely in General Chemistry 2, where we talk about specifically what are these beta particles and gamma rays, and how do we show them in an equation in which an element degrades or is radioactive. Again, that is not part of Unit 2. All right, this is, for my class, this is all I want them to know for Unit 2 concerning the nucleus and nuclear stability.